Hello, and welcome to the SMaRT-5G Introduction and Demonstration webinar. Thank you for joining us today. Today, we have an exciting lineup of speakers from ONF, Remito Labs, and Tieto Every, in addition to a demonstration. Now, please welcome our first speaker, SMaRT. SMaRT is the Chief Architect for Open RAN at the ONF.
All right. Thanks, Denise, for the brief introduction. I am Sarath Puthanpura from ONF. I'm the Chief Architect of Open RAN. And I will be starting off this today's discussion, followed by my colleagues, Marcin and Arne. So to start with, about me, I joined ONF about a year ago, and prior to that, I had a very long stint with AT&T for more than 3 decades, leading various teams in R&D, network planning, network implementation, and operations automation. And I've been a strong advocate of open source solutions. And under the auspices of ONF, I'm primarily concentrating on interoperability issues and, in particular, the sustainability issues as we face ongoing. So, to begin with a brief introduction about what's ONF current activities and how today's discussions kind of fit into the big picture. So, there are 2 major initiatives that are currently running in parallel for ONF. One is RRail, which stands for RAN, RIC, and Application Integration Lab. Is basically a collaborative environment or a multiple environment, some virtual, some physical, to check the interoperability and portability of application, which is very, very important when you deal with Open RAN solutions. And a bit of deviation from the prior, I would say, paradigm in which ONF is operating. This time we are, for these activities, we are considering both vendor stacks and open source stacks. And as the use case or various experiments permit or need, we will mix both. And we'll be seeing in maybe some of the discussions later. And today's concentration of the discussion is on SMaRT-5G. It's a sustainability initiative. What it entails is a series of POCs and trials for concepts and trials, and using both commercial and open source software stacks. And clearly, we need to try these POCs and trials and various, you need a place to do that. That's RRail. That's where RRail come into picture. So, if you will, you can consider that SMaRT-5G and sustainability related POCs are the first use case that RRail, and it's the most important use case that RRail is concerned to start with. And then once that is done, we'll probably move on to other aspects also. And with respect to the applications that's being used or that is being planned to use for this SMaRT-5G series of POCs, I'll go over that in a minute. And here also we consider both commercial and vendor applications solutions for this. So a brief discussion about RRail, where these all POCs are going to run. So if you consider this as separate environments or environments, both commercial software and open source software, they coexist or they support. So there are multiple swim lanes as you speak, and we are, if you look at, there's a different commercial environment, 1, 2, 3, and so on and so forth. And then and also we do have a pure OpenStack implementation environment, the open source stack implementation. The reason is that we thought that it would be conducive for flexibility and experiments before we kind of depending on commercial solution to test it in a hardened and a realistic way. An open source stack would be useful, and today's demonstration is purely on open source stack. So this stack is virtually implemented, so it's cloud native. And then we are in the process of making the first commercial RIC environment with the Powder Labs in the University of Utah. with simulator from Keysight, and then all the I shown not shown the SMO here to make it less complicated. This figure is already cluttered. So all the rigs and non-RT near-RT rig and SMO from Juniper Systems, and initially Eros Technologies is going to provide some applications to look at the sustainability. So that's being done, and also we started this discussion with I-14Y in Berlin to start another instance. So these things are progressing, and that and in the future, I would see kind of a couple more multiple locations and instances where we can do a very flexible and interoperable and interchangeable uh, setup. So coming back to the Smart 5G, which is the thrust of today's discussion, what Smart 5G entail is a series of proof of concepts, which is in a progressive manner. So if you look at it, the progression starting from left to right, energy saving can be achieved for the RAN and the core in multiple ways. So we start going with the most important one and also what is more implementable today. So one important thing about Smart 5G is that we would like to have the solution once it tested in the labs. We'd like to get it adopted by the operators, both for the traditional RAN and the Open RAN configurations. So as you know that 5G is being rolled out in traditional RAN more than anything else at this point. So there is a real need for having this solution available for the traditional RAN, and as the adoption progresses, we should be able to make the solution fungible for disaggregated RAN and open RAN or architectures. So starting from the left is cell on-off, which is the most rudimentary operations which have been talking about, people have been talking about for a long time. Even in the traditional vendors, there have been D-zone solutions available for that. How different operators are using the D-zone is a different discussion. Whether they're using it or so, that's a separate discussion. And we start with the cell on-off. And that will be the discussion today with from the technology that is being used and the demo that has been shown in the fields. So that's that, and then moving on to MIMO turn off. I mean both 2x4 to 4x4 no MIMO, or even massive MIMO. You can turn on some of the RF panels and the antenna arrays and so on and so forth. So that is the first two phases. And as I mentioned, we believe that these solutions would be applicable, or with the right adaptation can be applicable for the traditional RAN, and we are striving to see some trials going on in that facet. So as we move to when we have a cloud-based solution for the RAN, we could modulate some of the cloud resources also. For example, if you have 100 RUs and supported by 10 DUs and maybe a couple of CUs, when the RUs goes down proportionately, we could spin down some of the DUs and maybe CUs so that you can get additional energy saving. And then moving on to the core, if the RAN capacity is reduced to 30% or 50%, then you can proportionately again spin down some of the core capacity also in accordance with the RAN capacity that's being used. So in this context, we can look into some of the optimizing some of the computing resources also, like the CPUs. There has been capabilities given by Intel and other manufacturers where you can reduce the CPU power usage by turning down the voltage or a clock frequency, or even turning down some of the CPU functions of the low load, which is probably not necessary. So that's the next phase. So now then we are going to some more sophisticated sleep modes called the advanced sleep mode, where we need some low latency control operations. So until then, we can you can implement this energy saving with pure R apps from the latency point of view. But when you move to advanced sleep modes, then we need to address the low latency issues with the X apps and near RT and then complete pretty much what is being talked about by the community. So this is a nominal way of progressing, but if some operator is going to jump right into, say, to 3 or even to advanced sleep mode, that's fine. But today, when you look at the industry, the way the 5G is being rolled out is on traditional RAN, and maybe this is a kind of an average reference progression chart, if you will. But this is not cast in concrete, and depending upon the situation where any MNO wants to try various things, Smart 5G is open to that. But this is how we have been progressing, and we are at step 1 at this point. Now, if you look at the demonstration that was done just a couple of weeks ago in Fuse, it's a significant milestone. By the way, a white paper has been written with all these details, and it's available on ONF website. It's been co-authored by many entities, including ONF and Ramido and Tieto and other folks. So it's there. So what we have been demonstrating, and we demonstrated Fuse and will be demonstrating today, is intelligent cell plan. It's a RAP doing the intelligent cell on off, and which works in hand with the traffic steering XApp. Now, we can always, as suggested by the previous chart, we can always implement the traffic steering and energy saving on single RAP, but we decided to split in this way because we are addressing two important use cases: energy saving and traffic steering in one single demo. And that way we can show the interaction between the RAP and XApp, and also we can show all the pretty much all the key ORAN defined entities and the interfaces. So that's what we'll be showing here with some details about this applications. And I must say, the first time, at least from the ONF point of view, a good community has put together and brought it up to solution in a relatively short time. And as you can see in later discussions. So the demo components are pretty straightforward. I mean, you might already could imagine that we have this, as I mentioned to you, this is done on the R-Rail open source stack. There is no commercial, I would say, components involved. So first of all, we need a RAN simulator, and ONF has a basic RAN simulator, which is a part of its SD-RAN software stack, which comprises of the RAN simulator and the near RT rig. So that's basically from the ONF SD-RAN software stack. And then we added, of course, it has got an E2 interface. It has been there, and there's some demonstration was done also in the previous. So the E2 interface was already existing. Now we added on is the non-RT rig and SMO. Both came from ORAN software community, and the SMO is a derivative of ONAP. It's a lightweight ONAP instance, which a good job of ORAN software community has done a pretty decent job in getting that to levels fairly quickly usable. And and also we implemented this O1 interface. So if you look at it, it has got all open source stack, and the energy saving app and the traffic steering XApp was both from Ramido Labs. So Ramido Labs has provided these applications, with the Martin will be going through in details. And the whole thing was put together, integrated together in a nice fashion by Tieto Every. And Arne is there. He is going to explain in detail the demo. So with that, I'm inviting Martin to take on, and then please go ahead with your description and discussions on the applications and the technology used. Martin.
Okay, thank you. So thanks, and welcome everybody from my side as well. And my name is Marcin Dryański. I'm the CEO and co-founder at Remedo Labs, a spin-off from the Poznań University of Technology in Poland. And we are developing XApps and RApps. And in this particular project, we have used two of those that I'm going to speak about. But I will start with an sort of an overview of the use cases that are subject to the current aspects related to energy saving. And then we'll move on to the overall design that then lead to the particular XApp and RApp algorithm development. So, well, you can move to the next one. So very shortly, because already SMaRT has been speaking about this for a while, basically in Oran Alliance and in SMaRT-5G project, so in ONF, but also in the Memorandum of Understanding and the TIP, all of those are pretty aligned with 4 of the energy efficiency or energy saving features that are being discussed. So on the left-hand side, and the one that we are discussing today is the cell on-off switching. Well, it's pretty simple, but we'll get to that later on as well. The idea is that we switch off the whole cell if the capacity is low, and the important point here is that we need to have a coverage layer. So what means is that we are switching off only the cells that are the capacity layers, and that could be small cells, but they also could be additional carriers if we have a multi-carrier scenario. On the right-hand side, we have the second use case, which is RF channel reconfiguration, which basically is the most advanced in the sense of it's most used in the massive MIMO cases. And here, instead of switching off the whole cell, we can be a little bit more granular, and we are switching off some of the RF chains so that when the traffic is decreasing, we basically are decreasing the number of beams and thus the antenna elements, and also RF chains, thus reducing the energy. Now, if we move to the next two, so the next slide, also was mentioned by SMaRT. So we are sort of pretty aligned in those aspects with Oran Alliance. We have advanced sleep mode selection, where we go to even more granular approach, where we sort of switch off some of the resources in the time domain. So not switching the cell, but rather switching off some of the resources whenever needed for a slot or a symbol basis. On the right-hand side, the final one, which is related to the cloud resources. So here we are not moving on the radio part anymore, but whenever there is low resource utilization, we can move some of the network functions to the other cloud nodes and shut down those nodes. And with this, we're moving to the actual use case that we are exposing here in this particular demo and the first phase of the project. If you're moving to the next one. So the idea is basically that we are following the traffic load pattern, and we could split the area in the city, for example, into several pieces and analyze them separately. And we are assuming that this is a single near and non-arterial covering the traffic demand there and analyzing those, which could be separate ones, which in this particular case, if you're analyzing the left part of the area, we have a macro site and several small cells. And whenever there is an incoming traffic or increasing traffic load, we are switching on those cells if the traffic load is going down, and that's a city area, which means, or a city center area. In the evenings, then the traffic moves out to suburban areas so that we could save up some energy by switching off some of the small cells. And this is what we are basically aiming here. So if you go to the next slide, from the Oran Alliance perspective, for this particular use case, Oran Alliance in the use case document provided guidance on the different roles in the Oran architecture for this particular elements that are defined by Oran. And if you have a look at this particular sub-use case on energy saving, starting off from the top side, the SMO, and thus the non-RT rig as well, and thus then the RAP, is responsible for getting the data, but also getting the configurations. So what kind of cells we have, how many of them we have, which of them are coverage and the capacity one, but we also need to receive the information about what's the cell load, what are the energy consumption, what are the geolocation, and then the users, where they are located, and so on. And then the second aspect of it is that it decides or suggests, sends a recommendation down over O1 interface to switch on or off a particular carrier or cell. Now this, of course, needs to go down to the E2 node, but also there is a possibility to go with open fronthaul M-plane directly to the ORU. But here in our simulation, we are assuming that the O1 is connected to E2 node and sending the actions speaking about the recommendation to switching cell on and off. And I'm speaking recommendation in particular because it's not directly a particular signal that automatically switches off the cell. What needs to be done is we need to do some cleaning before we switch off the cell, which meaning we need to modify disable carrier aggregation, trigger some handovers, and then finally make the final decision on switching on and off in a particular part, which is then forwarded towards the open fronthaul M-plane, and then based on the actual decision, the cell on off commands go down directly to the ORU that are either switched on and off. And in the other sort of direction, the ORUs are sort of reporting the current energy consumption metrics. Now, having this one as a framework, then we moved towards the design of the whole sort of framework and algorithm that is taken part in this particular project. So if we go to the next one, the idea here is, remember, we had the city center part, and then we have an incoming or increasing traffic and decreasing traffic. Now, if you have a look at the right-hand side and there's a decreasing traffic load, then the assumption is that the energy-saving Arab is the one ruling the whole thing, having the most broad view on what's happening. And it basically takes two actions. First of all, it sends the traffic steering policy, because we need to move all the users out of the capacity cells to the coverage cells before we switch them off, so that the users do not lose connections and do not lose the particular SLAs. And then once this is done, then the capacity cells need to be off, which means that there are two actions in that particular order. So first we send the policy down to the traffic steering XApp that does handovers to move all users to the coverage cell. And then once this is done, the ORU is basically switched off by the second command from the energy saving Arab. On the other direction, and you can see on the left-hand side, when there is an increasing traffic load, we need to do a totally opposite direction in the sense of those actions. So first we need to enable capacity cells because there is an increasing traffic load that we need to take into account. But then secondly, in order to very efficiently and fastly balance the load and then distribute the load in the cells that are available, the new ones, we need to send additional traffic steering policy to make sure that we do that. So in that particular order, the energy saving Arab first switches on the cells. Now when they are on, then the policy towards the traffic steering XApp are invoked so that the users are distributed to those cells. Now, if we move to the next slide, taking this into account, we have the particular design here. So we split this into two apps, the energy saving Arab and traffic steering XApp. We use all the interfaces, so A1 to sending the traffic steering policy, E2 to send the actual handover commands, being the decisions of the traffic steering XApp, and then the energy saving Arab gets the cell load over O1 interface and sends the on-off commands over O1 as well. Now, the important point here is that we are seeing here the cell load on two particular places. One is over O1, and that is used by the non-RT-rig and the energy saving Arab over a longer period of time. And that's more of a statistics so that we know that the overall load is getting down. But then on the near RT-rig, we also take that into account, taking the E2 service models on key performance measurements, so that the traffic steering locally takes that into account to distribute the load evenly in a sort of much smaller time scale. So this is the overall concept. And now we have a look at each individual apps here. So energy saving app first. If you go to the next slide. So the energy saving app, as we mentioned, it treats the cell on-off switching, right? So the idea is to maximize energy efficiency. So to utilize the cell on-off to increase the energy saving, but in order to maximize the energy efficiency, which also takes into account the SLA and the throughput of the users, we need to monitor the traffic load, the current power consumption, and that is used with O1 interface. And then taking that into account, the decision is taken so that we can perceive or persist with the user's SLA. So once getting those measurements generates particular policies down to the traffic steering XApp. In that context, it is coordinating the operation of the traffic steering XApp via A1 interface and then sends the commands over O1 interface. And that is suitable for both the heterogeneous network scenarios with small cells and macro sites, but also in different scenarios where we have multiple carriers, for example. So now if you go to the next one, the important aspects that we already mentioned several times, but the important point is here that the energy saving app is coordinating what is happening with the traffic steering so that we have ensurement that the coverage is not down. So we need to make sure that we only switch off the capacity cells, and we also make sure that there is no degradation of service quality. Now, on the other end, the load-based approach, first of all, there are possibility to use multiple different ways to get the load, right? We could use the PRB utilization that is used in this particular setup, but we could also use number of RRC connections or quality of service flows, or combine those to get a little bit more granular and a little bit more insight of what we are doing with the traffic steering decisions. And then in order to avoid ping pongs, then we use separate thresholds for switching on and off of those cells. Now, important point here is that those in our particular scenario here are defined sort of based on the operator command. So what are the thresholds that they're expecting? But then in addition to that, what could be done is that those thresholds are selected by some machine learning models that learn when to switch on and off those cells. Now going down to the traffic steering XApp, so the next one, it is basically an algorithm that takes into account multiple different factors to take the ultimate decision. The decision that it takes is to move the user from one cell to another one, or in other words, sending handover commands directly to the E2 nodes. Now, it takes into account the radio conditions, so RSRP values, but also cell types, small cells or macro cells, the coverage or capacity cells, but also service types or quality of service profiles. The idea here is that we optimize user throughput and cell outage, but we also could take a different performance metrics. The important point also here is that it's composed of two functions, the load balancing and service-based steering. And I'm going to get back to this in a second. The idea also and the emphasis from our side is that it supports A1 interface. So we could control the behavior of the traffic steering XApp by A1 policy that was used in this particular use case. And it could support multiple different scenarios that we tested it with, macro only or heterogeneous networks, or with V2X scenarios that offload some of the traffic if there is high priority traffic or energy saving, or even mixed reality if we take into account another factor that speaks about the delay. And now if you go to the final slide from my side, the aspects that we are teaching and what I already mentioned that we are dealing here with is the load balancing and service-based association. So those are the two main functions of the algorithm. And then we could take one of these, meaning we only want to do the load balancing without taking into account what types of traffic we have, or we could do the opposite, which is the service-based association, meaning that we only want to move the voice users to the macro side and then MBB users to the small cells whenever needed. But we can combine those as well, or we can even do a per UE cell association. So we can take an individual UE and then associate it per our need. And those could be treated separately or together And then in addition to that, we could have a controllable behavior, meaning that we want to do more aggressive load balancing. We want to balance the load for whatever it takes, or we could do a little bit more smoother load balancing. Also for the service-based steering, it could be more aggressive, meaning we want to offload as much as possible, or we only do a slight offloading. So with this, I would like now to conclude this part and then move to and leave the floor to Arne, who will speak about what was done in the particular demo.
Anyhow, I shall try to take you through the details of the demo scenario and describe. We have a demo set up with a very rudimentary network with two cells, one considered as a coverage cell and the other considered as a capacity cells. And we have 4 UEs that are two on each, two of which are associated to these two cells. So then we can go on, Sarah, to the next slide. This I think we skip because you already talked about all this, so we can go directly to the sequence. The next slide. So this is the overall sequence. Not all components are in here, and it's of course simplified, but I think it will earn its purpose of explaining the logic of the whole solution. So we shall look into details of this stepwise. If you take next slide. So when we start all this, then we have a balanced network, and the traffic steering XApp has probably done its work good and spread out the UEs in the best possible way with respect to service delivery and cell availability and all this. We have just started the PM measurement in the RAN simulator, or in the RAN, and we will start sending up PM result files to the SMO, to the FCAPS part of the SMO. You can take next. And when it arrives, the file arrives, it will be forwarded to the non-RT RIC, and will be the file will be processed, and the information relevant for the RAP will be extracted and forward to the RAP. And this will happen in a loop continuously. For every PM file that is sent up, this procedure will go on. And as long as everything looks fine from the RAP's perspective, and we are not close to any threshold or something, then nothing happens. But then suddenly, the next slide, please. Yeah, then the RAP detects that we are below the threshold for the capacity cell, and will, by that understanding, the RAP will trigger a shutdown of this cell, and that will start with, if you go to next slide, that you install, the RAP will install a policy forbid cell for the capacity cell in the XApp. That will cause the XApp, as Marcin said, to do a number of handovers to clean the cell from this usage. And when that is ready, we can take the next slide. Then we will see that the forbidden cell is now not used, and all UEs are moved to the coverage cell. The RAP, energy saving RAP, will detect this situation by looking at the data regularly coming, the PM data, and we'll see that the cell is not used any longer, and will instruct the SMO to do a lock of that cell. You can take next slide. So it will then, the SMO will use the normal O1 interface to lock the cell, which will deactivate the cell in the radio, and in the end the radiation power will stop. So we have a situation now with a cell, the capacity cell is turned off and it's not used, and all users are with limited amount of traffic, because it's low level traffic camping on the coverage cell. Then when you can take next slide. Then we could imagine that the load will increase in the coverage cell, and our app will again on the regular data, PM data coming, will detect that and see sooner or later that we pass the threshold again in the other direction. You can take next slide. And that will cause two things, naturally. We will delete the forbid policy in the X app, and we will instruct the SMO to unlock the cell. That should maybe come in the other direction, but we could see it happen at the same time. And when you unlock the cell, you will activate the RU, and the transmitting power will start all over again. And next slide, please. Now we will go into a balanced mode again, where either the TS X app has done its work and rebalanced the load by handover. It's not shown in this diagram, or it will just be available for new attachment or new bearer setting up. It depends on how the load situation looks, if it will be explicit handovers due to that the cell is enabled again. So this is essentially what happens in the demo. Maybe you're disappointed that I wouldn't run the demo, but I have explained it anyhow. So SMaRT, you can take over again.
Now, just to summarize on where we are at this point. So these two two use cases are very important to the industry, and then we try to show this cohesive way to demonstrate, do it alone and one as a standalone mode or with a combination mode. So we purposely chose this mode so we can show all the interfaces, the interactions, and we can build upon that. So we are in the process right now to enhance this demo further. And the next steps are, well, for this particular setup is the demo is to be made available in other labs, and we are working with I14Y, for example, to do that. And we want to do this in a multi-vendor setup, in the sense that we are going to bring the R app from in the labs, and then Remido's traffic steering app. We just to see how two vendors, how they coexist, because as I mentioned to you, the most important aspects that we are addressing through these initiatives are interoperability and sustainability both. So sustainability is a use case, and in that one we'd like to show some interoperability and portability also. So the AML based R app from Intel Labs, we just trained on actual operator data, and then see if we can get some real life angles to this one. And also we are replacing the simulator with a more powerful commercial one from VRV Solutions. So this again as an example of we are kind of mixing open source solutions with with a commercial product from VRV. So, and that's what is being, as we speak, is being done. And also subsequently, we like to get into some field trials, as I mentioned to you, because one of the major aim for this whole SMaRT-5G is to make it usable for today's, I would say traditional network and ORAN compliant network. And the community is growing, and I urge, the participant here to join this exciting effort to move on to the next phase and get into some field trials, and then start, getting the benefits of these experiments and trials into real network, and then to manage energy costs and to increase efficiency in RAN operations. So there is, if you go to the ONF website, you can always join this community, and then we have weekly meetings, and then please, I urge the participant to consider joining this effort in this community. So with that, I'm going to look at some of the Q&As. Maybe I should stop sharing this, and there's some Q&A there. There is a question. Can give examples of these commercials and open source 5G stack? Is it a question, or is it can give example of? So I think the commercial stacks. I'll take this question. So if the question is to see what are the commercial stacks that we're using, we're going to plan to use, because we talked about VRV simulator and also Keysight simulator, and bringing the RIC and some more from Juniper systems, and possibly others. But the open source stack is, we are continuing to use the SD-RAN stack, and also we would continue to use the ORAN software community stacks, and possibly ONAP, maybe other versions of that. So I think the next question is, which open source simulator has been used? Are there any performance evaluations? The answer is no. The open source stack which we use is SD. It is called RANSIM. It is available as a part of the SD-RAN software package, and it's can be used by anyone without any license. And we don't have any comparisons, but clearly, obviously, when you move to something like VRV solution, is way more powerful, because we want to bring in some more real life experience to this one, and so that we can get into some trials. So the next questions are, what are the open source simulators you have used? I think I talked about it. What is SD-RAN? SD-RAN is an open source package from ONF, which comprises of the simulator and the NearRT RIC with the E2 interfaces. That's a question. Thanks for the next question is, thanks for the presentation. The demo, the employee setup uses ONF SD-RAN, but it had some upgrades regarding e.g. A1O1 interface. Will these upgrades be available to the community? Can we expect to the next v1.5 release for the SD-RAN to them? The answer is yes. The O1 is a new implementation, so this is available to the community. And with respect to the versions, Martin, maybe you can comment on that. Which version we have been using is v1.5, or which one?
That was 1.4 plus some additional updates for the new service models, but I believe the 1.5 is not sort of available.
Yeah,
for public domain.
Did I answer this question? So if any other questions, please. No open questions. No other open questions. So.
Okay, well, if there are no other open questions, I want to thank everyone for joining us today, and certainly thank you to our guest speakers, Marcin, Arne, and SMaRT. Following this meeting, everyone will get an email that includes the video recording as well as a copy of the slides. Thank you again and enjoy your day. This concludes our broadcast.
Thank you.